Okay, so what we're gonna do today is we're going to make things a little more complicated for you because I keep kind of abstracting away what we think about, right? Like I draw an AND gate up here. See if I can find a marker that works. That's better. Okay, so we get an AND gate, right? And we know that we can draw the truth table, and we know the output becomes a 1 or on if both the inputs have a 1 at them. And we know 1 is something like 5 volts or 1.8 volts or whatever the power supply happens to be, right? But what we don't know is what is that? What is inside of it? So we've gone the other way before, right? We had you build block diagrams where we even further abstracted this idea. Let's delve down instead and go look at what's inside. And what's inside is a technology that we call CMOS. MOS devices, this really just MOS, which itself is meaningless to you, but don't worry about it. You don't need to know what they are, how they're made, how they're built. You learn that later. We're going to start at a higher level of abstraction, right? That's what this program, your whole degree, is going to do to you. We're going to give you an idea, we're going to make it more abstract, and then we're going to delve down into more details, and we're going to oscillate back and forth until you know almost everything there is to know about the basics of electronic devices. Now, CMOS devices are built out of two different MOS devices, because CMOS is a type of technology that combines something called an NMOS. This is a FET, F-E-T, that is of type NMOS. There is a whole lot that goes into NMOS. These are what we call semiconductors, right? So when you start hearing the word semiconductor or semiconductor industry, one of the things they might be talking about is an NMOS device. The other is a PMOS device. It looks like this. Each of these devices have 3 terminals. Those little circles are not inverters, they're terminals. I know it's a little confusing in this class, but let's use it for now. Meaning a terminal being something that you can connect to, right? Somewhere where you're able to connect. We would also call this like a port, right? That's another concept we've talked about that would work. And all they are in the land of the digital world is they're switches, actually. This port is called the gate. Okay. And it's called the gate is because it allows current to flow between the other 2 terminals. That's all it does. Is if it is a 1, the NMOS opens. If it's a 0, the NMOS closes. So you got to think about it like a switch. Let me draw this the weird way, actually. I'm going to do the switch the opposite direction as I usually do. It looks like this. That's the gate. And voltage, if you like make an analogy between electricity and water, right? Current is the flow of water. Voltage is pressure. Okay, if I increase pressure on the gate, if I increase the voltage, it pushes that switch shut. Now, these devices are way more complicated than that. But fortunately, in the land of digital, we just get to pretend they're switches and forget everything else about them, which is really nice. Until you get to really advanced technologies, which I'll explain in a bit. But basically, the idea is, notice the switches you have on the breadboards, right? They're really big. That would not be very fast, right? The bigger something is, the slower it's going to go. both in the physical world, right? It's harder to accelerate a large truck than it is a small sports car. Same thing kind of works in the electrical world, which the smaller it is, the faster it goes. And as you know, if you've ever like looked at buying a phone more than, oh, I want an iPhone, and you've looked at like specifications, right? One of the things they brag about is how many gigahertz the processor is, right? How fast is the processor? That's what they care about. And part of making things faster is making the devices smaller, right? And area is expensive, so we want it to be smaller. So we have this device that can function as a switch, and now we can make things small, which means we can make them fast. And these two devices form the foundation of our world, our modern world. The foundation of every technology that we have in existence right now is built on the backs of NMOS and PMOS devices. There are other types of FETs, there are other behaviors that they have. This is what we're going to focus on. You will learn more later. Back to the CMOS idea, the C in MOS just means complementary MOS. Well, complementary because this is still the gate of the PMOS device, right? This is NMOS, this is PMOS. See the little bubble? This one is an inversion bubble. What this means is the PMOS device closes its switch when it sees a 0. So it's just negative logic, right? Active low circuit. And we've talked about active low. We don't do a lot with it in this class. We use it as control signals. But when we start looking at the innards of our AND gates, for example, these devices are what's in them. So what I'm going to do is I'm going to draw an inverter, okay? Inverters are the second simplest device that we've learned about, right? Because if I put a 0 on one end, I get a 1 on the output. If I put a 1 on the input, I get a 0 on the output. The only thing simpler is a buffer, right? That just takes a 1 and outputs a 1, gets a 0, outputs a 0. Well, it turns out in the design process, it is easier to build an inverter than it is a buffer. And we're just going to use this switching property to build an inverter. So let's say we have the standard circuit that we have, and I just replace the switch with an NMOS device, right? No switch, instead of an NMOS out here, I'm going to call this is our digital signal, right? It can make 1s and 0s. Because what happens is if I get a 0 here, then it's disconnected, right? The gate is not closed, current cannot flow, it's broken the connection. I have the pull-up resistor to VCC, and I get a 1. A 0 here makes a 1 at the output. I built an inverter, right? If I put a 1 here, the gate closes, it is connected, and now there's a direct connection through the switch to ground to digital signal, it's 0. It's an inverter. Well, it turns out that NMOS devices, through the magic of math and physics, have to be on this low side because they only turn on in certain circumstances, and it has to do with the relationship between the voltage of the gate and the voltage of this node down here. We don't really need to know that. We just have to memorize where they go for now. I'm going to make someone else teach you all the fancy math equations on how these work and behave and what the conditions are for turning on. I just want you to understand for now that these are switches that turn on if I put a 1 here, so long as the NMOS is close to ground. And the PMOS, I can build the opposite way. Like so. So if I put a 0 here, that means the PMOS closes, meaning it is connected between the terminals, because the PMOS operates the opposite of the NMOS, right? We know that in this little inversion bubble. So I put a 0. There is a connection between VCC and the digital signal. There's no path between them. It's just a closed switch, meaning digital signal becomes a 1. So I input a 0, output a 1, input a 1, output a 0. This 2 is an inverter. If I were to replace this with an NMOS, it wouldn't work. And I'm not going to get into the device physics of why, but it doesn't. So for now, just trust me when I say the NMOS go down here, the PMOS go up there, and everything works nice and happy. We're going to call the NMOS the pull down network, and the PMOS the pull up network, right? Because the NMOS have the ability to pull it to 0, the PMOS have the ability to pull it up to 1. But I already said that we like MOS devices because they're small. It turns out resistors of any significant size are big. It's hard to make small resistors in comparison to MOS devices. Since real estate on circuits, on your digital logic and things that are in your phone and the processors is expensive, and we want our phones to be small, right? These resistors are not good. There's another issue, okay? We want our phones to be fast, and we also want the battery to last a while, right? So there's an issue with this, where if there's a 1 here, that means current flows from power to ground, and we burn power on this resistor, basically, is what happens, right? If current is flowing, I'm burning power. If current's not flowing, I'm not using power. And this isn't like a foreign concept to you guys, whether you realize it or not, right? Is if you happen to be not living at your parents and you own a home or you're in an apartment or something and you get charged for electricity, right? You would not turn on your electric oven unless you're using it because it costs money, right? And that's because you have to pay for power. And the power only happens if it's on, and if it's on, that means current is flowing. If the electric socket is just sitting there, there's nothing connected between the two, there's no current, you're not paying any money because it's not doing any work, right? Power is work, essentially, or doing anything with it. So there's an issue here where if I put a 1 here and I close, this circuit is doing work all the time, even if I'm not using it, right? Much like the old adage about our brains that isn't really true, right? Computers don't use all of their processing power all of the time. And so we would like a situation where if they're not using the processing power, it's not burning power. So we could write really sophisticated logic that like always puts a 0 here to prevent any current from flowing. But that's not really a good solution because then it can't necessarily remember that there was a 0, right? You're basically resetting its knowledge every time. Well, it turns out if this is an inverter and that is an inverter, let's just smash the two together and get rid of our resistors. I now have in that splits into 2 wires, goes into the gates of a PMOS device and an NMOS device. All right, now let's think about what happens. Let's start with the 0. If I put a 0 at the input, well, 0 means the NMOS is open and the PMOS is closed. So what I get when n equals 0, my circuit looks like this. What is the value of digital signal? 1, right? Because it's connected right to VCC. VCC is our 1. We have an inverter. If I put a 0, if I put a 1, the PMOS device turns off, it opens, but the NMOS device closes. So I put in a 1, and now my digital signal is still in the same spot, but it's a 0. It's connected to ground. And so as long as we don't do something with the input that's weird and put it somewhere in the middle where they're both like half open, then as long as we put a 0 or a 1 in, then in neither one of those cases does any current flow, right? There's no path in either case between power and ground. We just save power. And we've got rid of this pesky resistor that is big and obnoxious, and we've made it smaller. This is a CMOS device. It is complementary because it uses NMOSs to pull down, PMOSs to pull up. They work together to optimize size and power consumption. Yes.
When did we start using these? These have been around for a long time.
Yes, like, I mean, I'm not great with the history part, but I think it was like 1960s essentially. Before this, they weren't really used in the 1960s still, right? Which is why you have like the vacuum tube televisions and stuff, because we used to use vacuum tubes to make this type of switching. Turns out those are really big and slow and clunky. And so when the MOS devices came, they started proliferating. And if you've heard the term Moore's Law, this is what they're talking about, actually, is the size of this device gets half, its size gets halved every, however often, I forgot Moore's Law right now, X amount of years, basically. And it's not really quite true. We kind of run into hurdles sometimes, and other times we have great leaps forward, but it keeps getting smaller and smaller and smaller over the year, which allows it to go faster and faster and faster. And now we have a runaway technology, and the rate of technological advancement is accelerating. Yeah.
Is there a theoretical limit to like how small these?
Yes. Yes, there is a theoretical limit to how small they get, because eventually you're running into a problem, which we have now. Right now, people are running into a problem in how do you build a device that is single. You have one atom thick, right? That's where we're bumping up to. That's the level that we've hit. And we are having issues around that because we're getting so small. There's not like a layer of material. There's just one little blip of semiconducting material. So yeah, we have issues. They've done some really clever things in order to make them smaller than they used to be. And really it just made them more dense, not really smaller. It's really a fascinating field. We're still a little ways off of getting to that being the real hurdle. Right now, the hurdle between getting smaller, I think I'm a little out of date on the semiconductor technology, because if you're not working it all the time, it goes really fast. But one of the issues ends up just being the manufacturability of it. And the other problem is from the designer standpoint of these guys get hard to work with when they start getting small. So I've done a lot of design in these guys in an old technology that is, we call it 180 nanometers, because the minimum feature size that you could make in that process was 180 nanometers. So 1 meter times 10 to the negative 9th times 180. So very, very small. Advanced technologies that are going into products are getting down to 14 nanometers, 12 nanometers, 7 nanometers. They're getting tiny. And now the issue is that these gates, remember how I say in an AND gate, no current flows into this gate ideally, right? Nothing, no current, but there is a little bit of leakage. Well, that's this. They have a little bit of leakage. They draw a little bit of current through them. It's not ideal, but the smaller we make them, the worse that gets, until you reach the problem they have now, where quantum tunneling becomes an issue, because the materials are so small that electrons can just go from here and appear over here because they felt like it, essentially. Yes, there's a real problem that's called quantum tunneling, where basically, I'm not a physicist, so if I mangle this, I'm sorry. The basic idea is electrons don't exist in a fixed spot unless you're looking at it. Other than that, they exist in a probability sphere, where there is the likelihood that it is at any given point in this region that is distributed around a circle. It's most likely to be in the middle, but maybe it's over here. And kind of what happens is every once in a while it decides that it's over here instead of in the middle, and it can do this through virtually any material as long as that material is sufficiently thin. So anyways, when I look at the 180 nanometer documentation to go make the chip, it was like 18 pages. It wasn't very long, right? To tell me how to design circuits using transistors that were 180 nanometers in their smallest dimension, essentially. When you go look at the documentation for 1 and 14 nanometers, it was like 800 pages explaining how to make these devices work. And it's hard, right? So that's one of the limitations is us as designers. It gets more and more and more and more to consider the smaller they get. Eventually we'll run out. Eventually transistors as we know them will no longer be the solution. And we're getting close, which is interesting because something comes next and you guys will be primed to be in a position to work with whatever that is, because it's going to be electrical. You're electrical engineers. It's interesting to see what's going to happen in the next 20 years. I have no idea. Okay, that was a little bit of a tangent. Okay, we build an inverter. Let's build an AND gate using the principle of pull up and pull down. Okay, which is to say, in the case of, and I'm going to switch this around because we had an inverter and inverters were easy. So let's do a NAND, an inverted AND gate. Which the AND gate, right, would have a 1 here and zeros everywhere else, which means the NAND gate is not the AND, which means I get a 0 and 3 1s. This is the truth table. And we know that the pull down network is responsible for the zeros. So we get to design this first by the pull down and then by the pull up. Okay, so what I do is I draw an NMOS. Let's start with an NMOS and let's call this signal A. If A is a 1, the NMOS closes and I want to come down to ground. But I need it to be 0 if A and B are both 1. So that means like that. We call this series. They're in a row. They're in a series, one after another, right? Like a television series, there is a sequence of them, one episode, episode 2, episode 3. In series, if A is 1 and B is 1, then this switch is closed and this switch is closed, and digital signal is now connected to ground. If either one of them is 0, it is nothing because it's not connected anywhere, right? This is where the pull-up network comes in handy. But the pull-up network is the opposite, which says if either A or B is 1 or 0, then I need to pull up. So because we're talking NAND, let's think in active low logic rather than active high. It gets a little bit easier. And let's just say if A or B is 0, output a 1. Right? Yeah.
So active low, that means zeros
On.
zeros on.
Yes.
Okay.
Yeah. So active low, right? If I have a signal S, and I say S dot low, that means this signal considers a 0 to be on.
And active high would be a 1.
Yes, exactly. Yeah, that would be dot H. If I don't write anything, we assume it's active high because active high is more common. And I prefer to do most of my design in it. I talk about active low because it's in the book, right? It's hard to read the book if I don't explain what they're talking about when you see this dot low. There is another notation that I think I've forgotten to tell you guys. So that's not S, right? Some books will do that, S tick. That's also not S because it's easier to type on a keyboard. That's all. Just be aware if you see this on like an online resource or another book or something, if you're studying that exists. Okay, so now let's go build our pull up. And what we want the pull up to do is use a PMOS device, call it A. Okay, let's do that. If A is 0, this one is open, it's off. If I have a 0, that guy closes and it's on. So now if A is 0, digital signal is 1 because I have broken the connection from digital signal to ground, so it can't be 0, and I have made the connection to VCC. But now I need to count for B. And B doesn't care what A is doing, right? If B is 0 on its own, it still wants to make that 1. So we don't want series because that would be an AND situation. What we need is an OR situation. Like so. I guess if I wanted to be a little bit less messy, I could probably do it this way. Right, that's the same thing because I was connected here and now I'm connected here, but there are no devices in between those 2 points, so they're the same point, they're the same signal, they're the same node, right? Does that make sense to everyone? That I redrew it, but it's the same thing. Okay, so now if either B or A is 0, then the PMOS closes and connects digital signal to 1. If they are both 0, well, guess what? There's just 2 switches in parallel. It's making this node the same value. If I have 2 different ways of making a thing 1, it's not going to break, right? If I was trying to make them different values at the same point, it would break, but this is the same value. So I'm just making it a 1 twice. That's not a problem. 2 different ways is fine. So A and B here, A or B there. Now, here's where we have to remember that PMOSs go up top, NMOSs go on bottom, because otherwise we're tempted to just like turn those into NMOS and those into PMOS, and I have an AND gate. Because this is NAND, right? And we would like to do that, but we can't because the devices just wouldn't turn on at all. They just wouldn't work right. It'd be kind of chaotic behavior. Anyways, so in order to build a AND gate, I just go plug this digital signal into an inverter, which we know is built like that. So in order to build a NAND gate, it takes me 4 devices. In order to build an AND gate, it takes me 6 devices. It is 50% larger to build an AND gate than it is to build NAND gates. Okay, this is why we like universal gates of NAND. This is why we learn to convert circuits into NAND gates, is because we want to save ourselves area and thereby saving costs. So if you design a circuit using the sum of products and you get AND gates that feed into an OR output gate, and then you draw the bubbles at the input of the OR gate and draw bubbles at the output of the AND gates. Now you have nothing but NAND gates, and you have a size optimal conversion. Make sense? So this is why we like it. Now we can do OR gates. OR gates are pretty, well, NOR gates, right? OR gates are going to have the same problem, which is it's going to be a NOR gate with an inverter at the output. And there's this kind of intuitive build to this, which is like OR is almost like the opposite of AND. Sometimes it feels like, right? It's just whatever an AND is doing, the OR is just counter to that. It's not quite true, but ORs have that feel to them. And so we can imagine, let's just build the opposite for the pull down and the opposite for the pull up, which is let's make a parallel pull down and the serial pull up and see what happens, right? So okay. This is a hard circuit diagram to digest, right? Because I just drew it up there and now we have to figure out what's happening. And it's all blue, which is hard to read, but this is how schematics end up. So let's take the opportunity to analyze the circuit, right? Analyzing a circuit just means let's figure out what's happening. How does it work? And we do that using a truth table. And this is, we don't know yet, right? We're figuring out what are we solving for. Well, all we do is let's apply these inputs. Let's go test these inputs. Okay. Put a 0 on A, a 0 on B. The 0 on A, that closes and that opens. Okay. The 0 on B means that closes and that opens. So what that tells me is if I have a 0, 0, then both of these are closed, which means VCC comes down here to our digital signal output, right? And because they're zeros, both of those are open, they're not on, so we are not connected to ground. We're good, right? We have made a 1. Now, let's go 1, 1, right? This is the next easiest one to do, is just both 1s, which means both of those are broken. They are not connected because 1 makes PMOS's off. Yeah.
So 1 will make a PMOS off, which means it's open.
Open, yes.
And then a 0 will make a PMOS
close, which is on.
And then is it just the opposite with the CMOS?
NMOS.
NMOS.
Yes. Yeah. Together they become CMOS, C for complementary.
Oh, okay.
PMOS up top, NMOS down bottom. PMOS acts like negative logic, NMOS acts like positive logic. Yes.
PMOS pulls up, right?
Yes, we will always use the PMOS as our pull up network. Which unfortunately there's no, at least I don't have one good like mnemonic device to remember this, because P pull up, but it's also pull down and now you're stuck. So I don't know, if you come up with a mnemonic, let me know, because really it's just these go down. And I will admit something, this is on video, this may be a bad thing to admit to. When I was an undergrad, you guys will often get choices, right, on which classes you take. And I think this program, you get 4 electives that you get to choose at the end. And the program that I went through, you actually got to choose what we call the junior core. So your junior core is signals and systems, electromagnetics if you're an EE. If you're a CE, there's like operating, it used to be operating systems, I think. I don't know what it is now. Anyways, you have these classes, but the program I went through, they just offered 5 classes and I got to pick 3 of them. And I did not pick the devices class because I was in what we would call signals. I dealt with communication devices and I didn't really care how they worked as long as I could use them. And so sometimes when I come back to these, I have to knock off the rust because I never actually took a course that taught about these because I had a very weird degree, which I will admit to readily. So anyways, if I get a little scatterbrained on this, that's why, is because it turns out as a digital designer, you need to understand just a little bit about how these work and then forget about the rest of it. Analog engineers is what I became eventually. This is why it's really funny, because eventually I became an analog circuit designer, which was designing at the transistor level and working in neural implants and designing circuits to go in rat brains, basically. And analog designers always make fun of digital designers because analog is like black magic. That's what everyone calls it, because it's really a mystery on how those things work because it's utterly insane. And so digital designers we just go type out a little bit of code and it plops out a circuit for us and we're done. Despite analog being harder, I made way more money as a digital designer. So it is what it is. You know, you have lots of paths to go through this as an electrical engineer. It's kind of fun as you march through the program, learning about what you're going to do. And on that topic, I strongly recommend going out now that you've started learning some, like especially if you have ECE 1000, now ECE 1270, and then 2700. Once you've got those core under you, you can go out and look for jobs. Just type electrical engineering jobs and just go read their descriptions, because you can start understanding at least some of the words that are in there, and you can see what electrical engineers do, right? And start tailoring your education and looking at electives to see what do you want to do when you graduate, right? Which is part of the fun of electrical engineering, is we are a surprisingly broad major. And even though people outside of our career don't really see that, they think we're electricians or something. It is a very broad field and it's a lot of fun. Okay. Enough of that tangent. Let's march on. Sorry, do we have a question? Sort of noise, it was odd. All right. Let's do the 1-1, because the 1-1 is the other easy situation. Well, that means both of those are off because they're inverted, right? That's what the bubble says to us, is it says if there's a 1, it's inverted to a 0, 0 being off. That's kind of what it's telling us. Well, a 1 here makes that connection, it turns it on. A 1 here makes that connection, it turns it on. They are both pulling to 0, therefore it's doubly a 0. Okay. Now let's go look at the 0-1 situations. Well, in this case, the pull-up network is really easy, right? Because if we look at the pull-up, if either one of them is 1, then the PMOS device turns off. It doesn't connect and it cannot be 1. And then if it is 1, then the NMOS does connect, it does turn on, closes that switch, and it connects to ground. And if either one of those does that, it is 0. Yeah.
So inside the PMOS, is that what's to the right over here?
Well, the PMOS does this behavior, but it's not inside of the PMOS.
Okay.
Yeah. I can actually, give me a minute. I'll come back to this.
No, I'm sorry. It makes sense now.
Oh, okay.
Sorry.
It's all right. So anyways, because they're in parallel, side by side, right? In parallel, you're going to hear this a lot. This is why I'm emphasizing it so much, is because if you're not an electrical engineer, parallel is a word that you don't use very often. But if you are an electrical engineer, it's like a daily occurrence. Same thing with series is a very odd word to use outside of television, but we're going to use it all the time. So parallel means if either one of them has a 1 on it, it connects digital signal to ground. I get a 0 at my output. All right, what is this? NOR, the NOR gate. If it helps, you can draw the OR, right? And there's some usefulness in being able to recognize what these devices are, because this is analysis. So we have now designed one and we have analyzed one. Yes,
So for an OR, we could just add an inverter at the end of it.
yes, exactly. Which would be this,
That's why we like to use MOS and NAND more.
because they are 50% fewer, or well, 30% fewer gates. Right? It's weird to go the back and forth because there's 50% more. Anyways, yeah.
Does the two NMOS on the bottom even matter? Because if either A or B is broken up top of NMOS, it wouldn't even get the signal from VCC, so it doesn't even need to be connected to ground.
It does need to be connected to ground because otherwise it becomes floating, which means we don't know what it is.
Okay.
So if we did the where we only have one gate, then the A would make it a 0, but the B would make it something, which it turns out most of the time that means it would hold on to whatever its previous value was. Actually, you'd have a very difficult time to get it out, basically, right? Because it's electricity. If I put a voltage somewhere floating in space and it has nowhere for the electrons to go, then it just sits and floats there in space, right? It needs somewhere to go, which is why your batteries don't drain very fast unless they are connected to something, right? That's what would end up happening, is it just sits and holds that potential that it used to be. And it acts like a really tiny battery because it's a capacitor, and capacitors work the same way. Okay. Let's say I apply the same principle and now I want to make a 3-input NAND gate. What do I do?
Just do, because NAND gets on the left, right?
Yeah, this is NAND.
Add another one more in parallel. That one more in parallel, and one more in NMOS series.
Exactly. We would have one more in parallel and one more, we would call it C, in series. And now I have a 3-input. And I would throw another one on and I would have 4-input. I throw another one and I have a 5-input. Throw another one on and guess what? It breaks. In fact, I actually don't know when this one breaks because it matters. Because remember how I said there's some relationship between the gate voltage and the other two nodes that needs to be satisfied? Well, the bigger you pile them up, the more voltage you need to make them all turn on. And so you have a kind of problem. There's a limit to the number of them that we can stack up. So let's say we could stack 4 of them before we break anything. Well, then that means in order to build an 8-input, I would just do what we did in homework 3, which you definitely all started, right? Which is we can build a 4-input NOR gate or NAND gate or AND gate out of smaller versions of those components. So that's all we would do, is we just start chaining these together and you can get a bigger bit of logic. And so then when you go and have a circuit, right, this is what we would call a canonical sum of products circuit. Canonical just means it's a uniform way of viewing things. That's sum of products. We would go ahead and do some bubble pushing, which, right, we would put 2 bubbles here and then slide one of them along each of those AND gates, and now I have nothing but NANDs. And so you could come over here and realize that, well, I called it X, Y, and Z, that one of those NAND gates, this is X, that's Y, right? That's the relationship between the NAND gates that we've been drawing so far and the MOS devices that we've learned about today.
Where's you were just drawing another.
I would have to draw another NAND gate, and then a third NAND gate, and then I could start wiring them together.
Okay, so like basically what's coming off the right would be what's going into the right hand NAND gate.
Yes, you are correct. And
That was below it.
and you know, this is actually probably a good exercise because I'm sure you're not the only one that wants verification. of what I'm talking about, right? Because sometimes it's helpful to actually draw it all out. I hate drawing things, but I can go ahead and this is normal to do. I just haven't done it in this class yet. Connect those together.
On the second one, you're going to use, but like,
X, Y, Y, Z. Right, I can do this, the representative, the virtual connections, because if this is called A, then that's also called A. So this is a fine way to draw it. Well, now I have my X connection, my Y connection, the other Y, the other Z. Let's do it again. Now we need to come over here and give these signals names, right, to represent that they are connected to something. We can go ahead and I guess L's in the middle of the alphabet. L's fine. Let's do M and N. I think is a little bit more distinctive. M, N. They get names M and N, which means that and I don't actually need to draw those because they are connected here. Yeah.
So that PMOS B at the top, would it be an okay thing to draw the pump going the other way, like pointing out?
Oh, you just mirror it
Yeah.
that way. Absolutely, totally fine. Yeah. In fact, sometimes you'll see them drawn horizontally.
So
Mine too.
they're not.
Yeah. And I will say at this point in time, I am choosing the most simplified version of an NMOS that I can draw, because there is more to these drawings of NMOS and PMOSs that we don't want to get into. But when you go, if you end up Googling like NMOS or PMOS and you see arrows that do something like this, I didn't forget it. It just is unnecessary, because if I draw it in the simplest form, there's this arrow tells us something actually, but you don't need to know what. It's just, it's implied that it does this if it's not there. These devices are so complicated. I almost think I shouldn't teach this here, but it is so helpful to dive in and know what's happening a little bit. We're not going to focus too heavily on this because I want you to know it, but these devices are so complicated that just explaining it, I start talking and I realize like, oh my gosh, how do I explain this? Because there's so much material to build up to it. And I get stuck sometimes. They are really cool though. And you'll get to work with them quite a bit throughout this program. Less if you're a computer engineer. If you hate this and you're a computer engineer, you're safe. Don't worry, you have to do way less of this than electricals do. Okay. Right. We have now built that circuit here using virtual connections, right? Symbolic connections. So we've just given them names, and we know that that X, sorry, this Y and that Y are the same Y, which is that Y because of the same name. Now, can anybody tell me why I call all of these A and B across them?
Because they're ports and not like the actual connection.
Exactly, they're the ports. I'm naming them the port A and the port B. So if I wanted to go call that out specifically, I would have the signal X is connected to the port A. The signal X is connected to the port A. On the inside, it views this port, this A, as A. But this A and that A are not the same because they are local. They're local to its little NAND gate that I have drawn. It doesn't extend out. Okay, this is what hierarchical design means, is I can give it a name in the local scenario, but outside just call it, hey, this is a port. This is something you can plug into. That's all we're doing. And if it helps, you can imagine that there is a box around each one of these with the associated ports, and these signals are on the outside. They're at a different level of the hierarchy. Okay, make sense, everyone? Cool. Now, let's take a new puzzle, a new situation that comes up fairly often, right? And if I'm designing something, as you notice when you build on your breadboards, the more wires there are, the more obnoxious it gets, right? And sometimes it is desirable to have as few wires as possible. Or in some situations, you have to kind of think very carefully about the way you're designing something, otherwise you run out of pins on a circuit. So like we have things called like microcontrollers, right, which you can program and they interact with the little world, the outside world, by putting ones and zeros on their pins. But if it wants to control many other devices or wants to talk to many other devices and it only has 16 pins, then I may want to consider, how do I limit the number of pins? So it's not uncommon to do something like use two-wire communication, which is saying two devices talk to each other back and forth, both directions, using only two wires, right? It's easy if I use three wires. One of those wires has to be ground because I need a reference. But the other wire, that's a lie, by the way, you're going to find exceptions to that down the line. But for now, you have one wire that is 0 volts. It's your reference. One wire that carries the signal that is going out to you. You each would have one wire that is coming back to me. Everything's fine. Because if I have the same wire and you're trying to talk on that wire and I'm trying to talk on that wire, then, well, the message gets garbled, right? And the other way of saying that is if I'm trying to send a string of ones and zeros and I have a 1 and you put a 0, then what is the voltage on that wire? Because over here it's a 1 and over here it's a 0. And what happens is you break both devices, right? Because if I close both switches, if I designed a bad circuit that closed both circuits, that means I have direct connection from power to ground with no resistance between. We have Ohm's law that says the current is proportional to the voltage divided by the resistance, right? V by R. R is 0, current is infinity, which means something breaks. Transistors. So what we do is some engineer somewhere back down the line got clever and came up with what they call open drain. It's called open drain. Word drain just refers to one of the ports on a MOS device. You'll learn more about that later, but it's called open drain. And I really did not need to erase that inverter. In fact, it would have been just fine. That's my output signal. And I want to say something like, okay, we only want to be able to assert zeros is how I'm going to phrase this, okay? Because what's going to happen is I don't want my circuit necessarily to be able to drive a 1. So we're going to use a pull-up resistor. We're actually going to bring this back because it's very helpful to have a situation where well, this is getting very hard to draw because my imagination sucks sometimes and I didn't print out the thing. Anyways, I'll start here. So, oh, not that. Okay, let's do that. This is my final output. Let's start here. This is a fine place to start. Now what happens? Well, this inverter, if it turns a 0, then this resistor pulls it up, right? So I get a 1 here. That 1 here is plugged into a gate. And as I said, gates have 0 input current, right? There's no current, which means no current is flowing through this resistor. It basically acts like a wire because there's a little bit, it's burning a little bit of power, but it's really trace amounts compared to any other situation. And now this circuit gets to do its nice job, and it can pull things from down to ground if it wants to. It has the ability to make this ground connect, right? This is what we call, well, this is the first step in what we want to do. Because, all right, I'm gonna pull up a diagram real quick to make sure. It would also be good to point you to the right direction, the right chapter in your textbook, right? To link this in so when you go and look it up, you know where to go. So, actually, by the way, have you all gotten the book? Has anyone not gotten the book yet? Is it still sold out there?
So they told me that they were ordering.
They're not ordering anymore. Raise your hand high if you don't have the book yet. Oh,
And they told me that yesterday.
great.
Yeah, I went in yesterday morning.
Okay. Thank you. I will puzzle something out. I'll probably just have to keep posting the chapters, I guess. So that's not ideal, but that's what we're gonna do. So this is chapter 5, which I think I've posted. Do we know? Okay, I'm gonna check that as well.
Yeah, you posted chapter 5.
Okay, great. Okay, so I'm gonna redraw a circuit over here to continue this one. These whiteboards are not easy to erase off of. Great. Okay, so the circuit that we're going to use for the first example, just so I stay on track with my notes. I guess I should just read the description, it's faster. I'm using a 2-foot AND gate. All right, that's easy. A, B, A, B. There we go. We've got a NAND gate, right? Because if A and B are both 1, it pulls it down to 0. And then if what we do is we plug this out, and we're going to do basically this, right? But we're going to do the same kind of concept where we're going to place the resistor with a PMOS device. And then, actually, I'm going to do something weird here just for fun. Let's go ahead and plug this guy into B for a second. And then we're going to go ahead and plug this guy into an NMOS device. And then we're going to call Y the output. Now, this is a very odd circuit. It's a very unusual circuit, but let's look at what happens. Well, the NAND gate, we know what happens, right? Oh, there's one more connection I forgot to draw, because this is the output, right? And this is going to go to that node. Nope, I did something wrong. Give me a second. I don't think I need this one at all. Let's try that. Okay, this makes that NAND, right? And now, if I get a 1 on this output, this gate turns on because I have a voltage from the gate to ground. That turns it on, and Y becomes 0. But I can't make a 1. This has no way of making Y 1. This is actually nice, because if I have two devices, we'll call it D1 and D2, and they have a 2-wire communication system. Well, then what that means is either one of them, in fact, we can even do it outside, just needs a pull-up resistor, right? Because if I add a pull-up resistor, then I'm back to the circuit that I drew first, right? And it will pull up to 1. And if both devices have this pull down, this open drain circuit, then either one can make a 0, but neither one can make a 1. So they will never find themselves in a situation that one of them is trying to make a 1 and one of them is trying to make a 0. It's that they are either trying to make a 0 or it's a 1. And then all they have to do is talk to each other, right? One of them will send a message and say, hey, listen up, here's this thing. And then it will go into listening mode, which is to say, turn this off. And so now, if I put a 1 here, it goes to 0. If not, it goes on. And now they can talk back and forth, time sharing one line, both directions. This is why we like open drain. This is all we add to the circuit. I way overcomplicated it just a second ago, but it's just doing this. We're just tacking on one of these where we're going to have a resistor that can pull to 0, or a resistor that pulls up to 1, or a circuit that pulls down to 0. And you're going to design, well, you're going to build an interface between two devices that do this in ECE 3610, the digital systems that fall into this course. Is we'll actually go and implement this in the real world. We're not going to get there in this class, I don't think, because it's a little complicated to actually implement, but the open drain thing is very useful to make these devices talk. I will not, I'm going to say I was going to say probably not, but I'm highly confident, like 98%, that I'm not going to ask any questions on the open drain part, because I'm going to deal with more of that in ECE 3610. Yeah. The most important part really is going to be the analysis side of this. Is if I give you a more complicated, not very much, I'm not going to give you more than 6-ish transistors and just go through, throw out a truth table, right? You'll have like 3 inputs, draw out a truth table, see if it's 1s or 0s. And the question might be, is there a situation where it can be both, the output is both 1 and 0? And then hopefully not, but if there is a circuit one, and then say there was, and then I would ask the follow-on question would be something like, what happens if you do that? Or the question could simply be like, given this circuit, if I input 0, 1, 1, what is the output? And then the output might be undefined, right? That's kind of both 0 and 1 at the same time, and it breaks. That's all we really need to understand about this. Yes.
The NMOS, when A1 gets pushed up against it, it's going to turn into, it's going to close because the pressure is pushing it.
Yeah, the pressure of the pressure, right? This analog, the voltage, yeah.
So then a PMOS doesn't have, because there's an inverter, so it feels pressure, it's kind of basically pull that lever open. I mean, if we're thinking of.
If that helps you, yes.
Okay.
Kind of the device physics of what is actually happening is not bad. It's just whether or not it lets current through. They do the same thing. It's just a different type of material that reacts in different ways.
So if PMOS has a one hit, come into it, it's gonna stay open.
Yeah.
And with an NMOS, it's gonna close.
Yes. Yeah.
You said something about a device having both 0 and 1, but if it's one device, how can it have two outputs? Or would it have to be two devices?
So let's say we went and designed a circuit. Yeah, this is fine. This needs to be PMOS. A, B, A, B. Let's say I gave you this circuit. And then I asked the question, what happens if I give you the input A is 0, B is 1? What is the output? What is the output Z if I have A equals, did I say 0, B equals 1? Well, if A is 0, this closes. And this is a really good way to do this analysis is just start redrawing the circuit, right? Is I can just be like, okay, here's VCC, the switch is closed. A is 0, that switch is closed. B is 1, that switch is open. Right, this is a great way to do this analysis. Now it comes down, that's my output Z. A is 0, so this branch is open. And that branch is closed because B is 1.
Mhm.
So what is my output Z?
Definitely 0.
It would like to be 0, but it would also like to be 1. Because I have a path from power to Z here. And I have a path from ground to Z here. So Z is now both 0 and 1. Oh, this is a bad circuit because I can accidentally light this thing on fire and break it.
Oh. I'm sorry, I might be thinking about this wrong, but isn't the power supposed to flow from up to the ground?
Yes, and that's really what it's doing, right? Is it's flowing into this same spot. So we're going the voltage VCC is being applied to this whole wire because that wire is one node. It's all the same voltage, but ground is 0 and connected to this whole node, and VCC is power and connected to the whole node. So VCC is trying its hardest. It will put every ounce of energy it can to make this 1. This path will put every ounce of energy it can into making it 0. And now they're fighting.
Okay.
And so it breaks.
That way you have to have one in parallel.
Yeah, I need to have one of the pull up or pull down has to be in series. Because you don't want a situation where some combination of inputs does this. And in this situation, it's really easy to recognize, right? I could go ahead, like on an exam, and ask you to analyze a circuit. As I said, I could draw like a real life XOR gate up here, and then you wouldn't know what it is because I haven't shown you, but you could go through and puzzle it out and get the truth table and you'd be fine. That's all you have to do with that. There is one more device that I want to talk about.
So I understand that the power and the ground are fighting, but like on the other ones, it's like, I don't know why I'm struggling to understand that when it's not connected to ground, it can be one, but when the ground. Like when you're having like a proper one.
This guy.
Yeah, how like you can be disconnected from ground and still get a phone signal.
So let's do a situation where what's an input combination that confuses you how it gets the result?
It was just like any way that for at least this one, because if you say 0, 1.
Okay, so A equals 0, B equals 1. Okay.
Because like at that point you got the signal from power being 1, and then you get an open circuit to ground.
Yeah, so let's just draw it, right? Let's just draw it with switches because this is a good analysis. A is 0, that makes this closed. B is 1, so therefore, oh wait, sorry, you said closed. You said the right thing and I messed it up. And then this is open. I just ruined your whole life, yeah. What is he doing? And now A is 0, so this is open. And B is 1, so that's closed. This is the circuit.
Right, so like that, the fact that they open and close differently makes sense to me.
Yeah.
But it's just like how Y would be getting 1. And like, but the fact that it's not connected to ground is what's like.
But because if it was connected to ground, as happened over here, it lights on fire. Because 1 is VCC, right? That's power. That's why we think about AND gates that way.
I guess that's just what I'm getting confused about. It's like with the circuits that we made in lab.
Yeah.
As soon as the ground wasn't connected, it didn't.
Yes, because these devices, they're not really switches, okay? And so what happens is there is a relationship where I've really tried to avoid writing this equation and I surrender. Let's do it. This is what I get for thinking I know how to simplify things better than every textbook that's out there. So in order to be on, there's the gate voltage, VG. And then we have the source voltage, which is going to be the bottom one. That's the source. One of the nodes is the drain, the other is the source. So VG minus VS has to be greater than some threshold, some amount of voltage, okay? This is the condition for turning on-ish, okay? Under certain conditions. There's a bunch of qualifiers to it. Well, let's go with this equation. We're digital engineers as far as this is concerned. We're lazy. We don't consider the analog effects. It's on or off, okay? So VG, gate voltage, if this is 1 and VS is ground, and as long as VTH is less than VCC, so let's pretend VTH is 0.7 volts, pick a number, right? 1 is 5 volts in our case, right? So it's really 5 minus, and in our case, it is probably not 0.7 volts. I mean, it could be like 2 volts. This is fine, right? 5 is greater than 2, it is on. However, is that true?
Yes, sir.
I don't know. That's what happens when you don't connect ground at all. Is because the switch is a little bit of a lie, right? Is because this device here is actually always connected to ground, and this node is not actually separating. It's just not letting electrons flow through it.
Gotcha. Cool.
Yeah. So it's just we're throwing in I don't know, which is why it gets so confusing sometimes, is because sometimes it works the first time because you have no voltage here, but because it's just kind of floating, you're not holding it to ground, then it drifts up to a higher voltage, and now it's no longer ground and it stops working. So you can have actually intermittent functionality.
I guess what I should have been thinking about how they're actually drawn.
Yeah.
Symbol is drawn rather than what it looks like per se to help us see it.
Yes. Yeah, I get that now. I understand.
Because like how it's drawn, it is always connected.
Yeah.
But like, yeah.
You guys don't need to know this equation yet. You will come to hate this equation. Unless you, that's not true. I shouldn't judge. Like sometimes I get annoyed about things in certain classes, but everybody hates different things about curriculum. Like some people love writing classes and some people hate them. It's fine. I have a bias towards certain classes. Like I am awful at electromagnetic, so I don't like them. It's not that it's a bad field. If you go and do electromagnetics, good for you. I'm terrible at it. Okay. Oh yeah, one more device that I have to cover before we move on. So let's say we have this device that I just drew up right here. This is going to be what we called an output enabled inverter. Output enable just means an inverter that has a third pin on it that has the ability to turn off the output. Okay, that's useful. So its truth table has the output enable and a, call that F. Now I get to introduce a whole new thing they get confused about. So in the case of an inverter, if I am enabled, if I have turned this device on, what does an inverter do? Well, it looks at the input A and just does the opposite, just like it always has. However, if I set 0 to the output enable, it is turned off. Which, how do we write that? Well, we write a Z. The reason we write a Z is because there's this term that we call impedance. Okay, so we've talked about resistance before. Impedance is basically the same thing. It's just that impedance changes with frequency and resistance doesn't. And when I say frequency, like our power lines, right, the things that power this building and our homes and everything, oscillates up and down at 60 hertz. Okay, this is AC power alternating current with a frequency of 60 hertz. There are some devices, including capacitors, which is the one that you're most likely familiar with, that block electricity differently depending on how fast it oscillates. This is all impedance is talking about, is resistance over frequency. Okay. So when I write high Z, I really mean high impedance, which is like high resistance. But high impedance just means it is disconnected. I have severed my connection, which is very similar to why we would want to use the open drain, right? Which is, we could use it for two devices to talk to each other without risk of breaking each other. So now we could picture, how do I want to do this? I'll skip that. Let's say I have a NAND gate. we know what the transistors, the FETs inside are doing, right? We could draw this. We have drawn it. And it wants to talk to another device. There's another device over here. And they want to share a wire. They want to talk to, there's another wire somewhere that's ground. They want to talk to each other. Well, the outputs on these don't really work as inputs. You can't really do it. So what we do is we branch the circuit and it goes into the other device. And there's some special circuit for listening. And then this is the talking device. And then, well, this doesn't work yet because if they can both talk at the same time and they could break for the same reason as previously. So I have a signal called enable. In this case, a 1 is going to turn on this NMOS. This inverter puts a 0, that one is off. Only one of these can talk at a time. We've solved the problem, right? A little bit more elegantly. This is all an output enable is doing, basically. There are other ways to build it. There are certain situations where doing it that way won't work. You don't have to worry about the details. Mostly, I want you to keep in mind that output enable has this truth table. We could even have output enabled NAND gates. It would be just a NAND gate with like another pin called OE, output enable.
It just causes some of the outputs to just like just disconnect.
Yeah, this goes to high impedance, which means just pull the plug, which is like it's an open switch, right? Which means it doesn't see it. So like this case, let's say that there's a third device down here. And this device sometimes want to listen to this NAND gate and sometimes wants to listen to this NAND gate. And so it sends out a signal called enable that tells it when it wants to talk to which one. Make sense?
Does that mean the inverter would flip so that it would turn the opposite NAND gate off?
I mean, if I wanted to, I could turn it around, but I don't have to. But what happens, right, is right now, if it puts it out a 0 means I want to talk to this device because a 0 gets inverted to a 1, turning on this guy. And 1 comes around, turns on this one, gets inverted to a 0, turns off that one.
So if the NAND gate on the side was putting out 0, another one's putting out.
If this is putting out a 1 and this is putting out a 0, it actually doesn't matter because you will always have a situation from the switch perspective that looks like this or
That works.
that. Yeah.
Yeah.
Yes. Yeah. That's all output enable. Output's really easy and very helpful. And now, as I've mentioned before, it's always really funny because like I teach a day class and a night class and you guys basically get 2 lectures. So sometimes like today in the middle, we're going to get a jarring shift between topics. This was lecture 5. We're moving on to lecture 6 now. So give me a moment while I begin to erase everything and gather my thoughts for lecture 6. Which I like much better than this lecture 5. This lecture 5 is my least favorite one. I'm not going to lie. Sorry, what was that? Speak up, let's hear it, come
I
on.
said, yeah, lecture 5 sucks.
You know,
That's great.
I won't take personal offense at that one. I don't know why I can't get these transistors to stick in my head. and it makes me scatterbrained more than usual.
And it makes more sense to me now than it did 2 hours ago.
Are you sure? Because 2 hours ago you didn't know it exists, so you're less confused, right? The first step in engineering is always to make you more confused before clarifying. And it's okay if you walk out confused, because I'll give you some simple homework problems. I'll go write them today or tomorrow, and we'll run through a couple of practice and it'll make sense. And then you'll forget about it until your junior year when you take 3110 and it comes back like, oh my gosh, I hate this. And then hopefully Dr. West is teaching it. He's an absolutely wonderful professor. If you haven't had him yet, he will embarrass me and he will make you like transistors again. Or he'll make him hate you, or make you hate him. One of the two. Anyways, Dr. West is great. He does like robotics and he does everything. He worked in it forever. Anyways, you have something to look forward to with Dr. West. Now, we're going to make gates even more complicated, okay? I need to make sure this is actually a lecture that I'm supposed to do. I have a calendar for a reason, guys. We'll come back to this. I think we've had enough like mind bending, making things more difficult. Shall we have a lecture that makes things easier instead?
Please.
Okay, let's go the other. This is like my favorite lecture. So we'll skip from my least favorite to my favorite lecture. So we've talked about simplifying circuits, right? Using Boolean algebra, and it's really helpful, but Boolean algebra is kind of hard. Have you guys started doing the Boolean algebra homework yet? Any of you?
I started it and then I cried.
Sounds about right. You should get to it sooner rather than later so that Boolean algebra isn't too far behind this lecture-wise, right?
Have time to cry.
Yeah, so you have time to cry. Some of you may have gotten a Starfish notification, right? That says you didn't have a submitted assignment. It's Canvas's fault because it like reassigned the due dates. And then I have a little thing that goes and checks if everyone's turned in lab 1, because if you haven't turned in lab 1, you're behind. But Canvas doesn't agree. Anyways, that's all that's happening. Is I don't want you guys to start falling behind, because it just kind of cascades and gets more and more problematic, and then you don't pass, and then I'm sad for you because it doesn't make me feel good for you not to pass. Anyways, so all I'm saying, start your homework on that. I'm going to assign another one if I have to at some point, right? I give you a full week to do it. I may end up assigning a homework that doesn't give you a full week just to force you guys to get back on track, because some of you are deviating a little bit much for my comfort at the moment, because I want to make sure you're on top of things. Now, the reason I'm talking about Boolean algebra is because it is something of a nightmare. You guys don't quite fully appreciate that nightmare if you haven't done the homework yet, but you've seen me do it and you haven't gone through the motions. But there is a better way of simplifying circuits, and it's called a K-map. And the nice thing with the K-maps is you can then actually go use them to verify that you did it right. Okay, you can check your Boolean algebra with a K-map. However, in the homework, you need to answer it because I say simplify using Boolean algebra. Okay, so I need to see that you know how to do the Boolean algebra, so that I know that you understand that process before you go and use the ECE tool, which is a K-map. Now, what a K-map does is it utilizes the concept of logic adjacency in order to say, well, maybe there's a way to visualize logic adjacency. That'd be really cool. That would be really useful. So the K in K-map stands for some French guy. Carnot, Mr. K. K-map. So let's say we have a truth table with inputs A and B. Actually, I'm going to do 3 inputs. The 2 variable K-maps are really weird, and I feel like it's an odd place to start. And F is a good output. Let me chill the chatter there. Thank you. It's distracting. Which means we need 8 rows, right? 2 to the 3 rows. 2, 4, 6, 8. There we go. Truth tables. And then I can generate a random function f. I don't really. That sounds fine. I don't know what this function does. Actually, maybe we should do something fun that actually makes sense, right? I guess good examples. We did prime before. We did that prime number detector before. I used that as an example while back.
Like that number's prime.
Yes. Let's detect if the number represented by ABC is a prime number. Right, and these rows, each of these, doing this trick just creates binary numbers from 0 to 7 is all this is doing. So 0, 1, 2, 3, 4, 5, 6, 7. And then we go prime, not prime, prime, not prime, prime. I never remember if one is prime or not. Because one is itself, it's like one and I think so. Let's go with this one. I like the extra one run away or another. So what this is saying is that P will be 1 if the input ABC is a prime number. Okay, this detects or asserts a 1 if there's a prime number. Okay, and we could go ahead and design the circuit using a sum of products expression, right? And we have the sum of products expression. One second. Yes. Sorry, I have to look at the calendar real quick to make sure that this makes sense. Did I introduce to this class the expressions for sum of products, like the sum terms?
Yeah.
Okay. I had a moment of panic where I was like, did I skip that part of the, okay. All right, so what we can say, right, this P is equal to the sum of the min terms 1, 2, 3, 5, 7. 2, M3, M5, M7. Right? Good. Cool. And then we go and say, that means, well, min term 1 is that guy, and prime is equal to, we know each min term needs all of the input variables. One, two, three, four, 5, 1, 2, 3, 4, 5. And now it's just a matter of going and finding where the zeros are. So min term 1 is not A, not B, C. 2 is not A, B, not C. Min term 3 is not A, B, C. Min term 5 has a not B. And min term 7 is A and B and C.
So if you were to put like a solid line over A and B, like in the first term,
Yes.
would that be
Wrong.
change it into like a NAND for A and B and C?
No, so you'd end up with a completely different expression.
Okay.
Yeah, so you got to be careful with that because not A and not B is not equal to.
The right side would be, would that be what like a you'd write as NAND?
That is a NAND gate, but this is not a NAND gate.
That would be
Our truth tables, right? We can just go figure it out. Well, where is not A and not B? Here's a 1. There you go. What is it? It's an R. So that would be a NOR gate ANDed with C, but we'd rather, this is just a 3-input AND gate, really, right? Because that's what a min-term is. This is a canonical form, meaning everybody will understand what you've written if you write it in this form. We get that, and then we start looking for 2 of these terms that are logically adjacent because they will simplify using Boolean algebra. So I go and look, and I say this and that are logically adjacent. This one and that one are also logically adjacent. Not A, not B. I think this one and that one, because only the B variable changes are logically adjacent. So I can then pull that one away so that I can use those two together without having a redundant term. And now I have this one. Do I have any that are not A, B? Not A, B, not C. So those two are the same. So that guy and that guy are the same. So I'm going to use that one twice, right? Because A and A is equal to A. Or sorry, yeah, A and A is equal to A. It just says A or A is equal to A, right? We can redundant terms. So I would just add an extra not A, B, C so that I could simplify. And just for a quick example, let's look at those two. And what happens is the not A and B factors out, and you have not C or C, which is always true. So it drops. And then we can go ahead, and now we can just play the game of just writing. So sorry, that was these two. Now I can play the game that these two, what changes, it's the B. So I have not A, C. Now that's done. Or, well, these two pair up, I don't have to add any extra terms, and the thing that changes is B, so A, C. I look scared and confused.
A little bit.
So all I've done in this one, each one of these is I've identified two terms that are logically adjacent, which means only one variable in each term is different.
Right.
So here, that's the B, because A, C, not B, B. B is what's different. So when I factor out not B or B, that's the only thing that's different.
Okay. And so when you said you're adding terms, were you just doing that in your head? And then...
Yeah, I was just pulling out two. See how I marked that pair,
Yeah.
that pair, and that pair? I just pulled out one pair at a time, just removing the thing that was different.
Okay.
Because the thing that's different doesn't belong.
Right. That makes sense.
Yeah. So now I have that, and now I have this. That goes away, which is C or not A, B. We're good. We've simplified it, right? That's Boolean algebra. Logic adjacency is a wonderful thing. Starting with sum of products makes Boolean algebra very, very easy. When I don't start with Boolean algebra is when it's harder, right? Because then you end up doing things like De Morgan's theorem. Yeah, you'll do it. You'll get practice. It'll be on the exam. Make sure we understand. Now, K maps. Are we okay with both colors, red and green? Can you see these guys? Okay, I just want to check. Sometimes things happen.
Question real quick.
Yeah.
You said that you like things alphabetized, like on the homework.
Yeah.
Did you switch those two just to make it easy for you?
Oh, this is actually okay. It's mostly inside of each of the variables. If you do switch it, I'll be even happier. But I'm not going to be too upset at this. It's when I get that is really hard to tell when I've graded 48 papers that those two are the same. Right? It's just a numbers game. There are a lot of you guys. This is going to be a really interesting lecture because by this time, this is normally the lecture that I introduce midterms because this is when the book introduces midterms. We already know what they are. So I'm curious to see how this goes. I've never taught the class quite this way. So I'm not completely insane. This is just kind of a new way of doing things for me. I'm sorry dragging you through this, but I think it's better because I think you feel like an engineer earlier than you would otherwise, which is why I've done it. This, you're going to see a lot of these. This is a 3-variable K map. The way we work with variable K maps is, see how there's 4 across? That means there's 2 variables that are going to be affiliated with that. I may end up erasing this and changing the order, and you'll see why in a second, but we're gonna go for now. And crap. Sorry. Normally by now I've also taught number conversion. There is a new type of counting that I have to introduce, which is there in this case strictly to capitalize on logic adjacency. So what it is it's gray code is what it's called. The name gray, not the color gray. And all it does is this is the number 0 in binary, right? We kind of know that by now, even though I haven't explicitly taught it. This is the number 1. And if I write the number 2, it is no longer logically adjacent with the number 1. And that one is. Now as I count, all of my numbers are logically adjacent. And in fact, it wraps around with logic adjacency. It is actually circular logic adjacency. Okay, this is all, that's all gray code is. It's just gray mapping. And we're not going to count in that yet. We're not going to deal with any of that. We're just going to utilize this in the K-map. And the reason is that I'm going to use this K-map to look at the min terms and see visibly which ones are logically adjacent. So the way that this works is saying 0, 0, 0, 1, 1, 1, because we're going to gray map. This is very, very important that you gray map your, or grade code your K-maps. Very important. If you flip this to 1, 0, now these two aren't logically adjacent, and it's hard to see logic adjacency. So 1, 1, 1, 0. This only has 2, 0, 1. Okay. Now, all I do, this is the same thing as saying not A, not B, not A, B, A, B, A, not B. And in this column, it's not C, C. Okay. These are the same thing. It's just in the top left, I'm saying this is what these numbers are associated with. So that these guys are A and this guy is B, right? That's the map that we're dealing with. Okay, so now what we do is we just go and look at what is the min term, not A, not B, not C. It's 0. Now I go and ask, what is the min term, not A, not B, C? Well, here I have not A, not B, C, and it's a 1. Then I have here, not A, B, not C, not A, B. Let's say it's not C, right? First, 1. The next one, not A, B, C, 1. Now I have to skip a row, right? Because this is A, B, C. Well, this one is. So we're going to jump over to here. Because so far I've just been marching down. Or now I'm at A, not B, not C. A, not B, not C. 1. Nope, 0. 1, 0, 1.
You're just copying the ones and zeros from P on the side.
Yeah. So the next time, once you write these in the right order, when you map it this way to that version of the K-map, then all I have to do, one second, I'll get right to you, is look at the row and just say it is 0, 1, 1, 1, 0, 1, 0, 1, and I just go down the row. I don't have to think about what every row is. However, if I flip the order of K-map and I do, this is perfectly allowed as long as I write them in the right boxes. Because I've reordered my columns, which is also allowed as long as you stay consistent, right? It's just about consistency. So that's why I said I may rewrite this, is because if I got off on a weird direction, then I wanted to change the order of my variables so that I could do what I did the second time. I like it to be easy, and I will redraw my K-maps in order to make it easy, basically. Now what this is saying is this one and that one are logically adjacent. This one and that one are logically adjacent. And this one and that one are logically adjacent. And guess what? Because gray map is circular, this one and that one are also logically adjacent. It wraps around. Logical adjacency does not work diagonally, right? Because this one and that one are not logically adjacent. So that means they can't simplify. We know they simplify if they are logically adjacent. So the way that the K-map works is once we've drawn this, we've done like a third of the work, about a third of the way there. Now we just go and start drawing circles. And I say, hey, look, those two guys are logically adjacent, so I'm going to put them in a circle. Now there's something even cooler. Because all four of those are logically adjacent to each other, I can circle all of them together. They cooperate to simplify. It's really helpful to have many different colors in these K-maps to keep track of your circles. Your circles are things that we call implicants. I strongly suggest when I go and post this chapter that you go and read it, because it's not posted yet, but I will post it. If I forget, email me. Because it's going to have this whole spiel on implicants, because there's different kinds of implicants. I know you've had it before. Do you remember the different kinds of implicants? You've done K-maps.
I don't remember.
You don't? So implicant is any valid circle that you can draw. However, there are prime implicants, and then there's like a something prime implicant. Sorry, I was not, whatever. Anyways, essential, that's what, the essential prime implicant. The most important word to know is implicant, and the second most important thing to know is essential prime implicant, and then the regular prime implicants, just throw them away, I don't really care. And what that's saying, essential prime implicant, is basically saying that I drew this picture in as few circles as possible. Because it is also valid to do these two and those two and those two. I have 3 circles. Because in order to ensure that I am minimizing all of them, I have to encompass all the ones inside of implicants. If I leave them out, then that means I forgot to bring them down. That's all that's saying. I had a question there.
I was just wondering, so if you had like on that bottom row of the K-map, if you have one in the first and in the last, could you circle those two with zeros in between them?
If there are 0 between, you can't
So
circle.
like there's one on the far left, one on the far right. Can you draw a circle between those ones? Since they're,
Far left, far right?
yeah.
Yes, you can absolutely do that. Yes,
You're just looking for the ones.
just for now. We could do the zeros instead, but for now we're going to worry about the ones. You had a question earlier that I forgot. Okay.
Are the boxes, so it's logical adjacency is what you're saying. Is that tied directly to like one axis, or if you have like a 2x2 square of ones, can you circle?
You can do
all
that too,
Okay.
and we will get there. I will do lots of examples of K-maps. Yes.
So if you were to do like have more inputs and everything, so it was instead of like a 2x4, it was bigger.
We will build up to 4, 5, and 6 variable K-maps.
Is there a limit to how many ones you can circle at a time?
There is a rule to the number of circles that you can do, but not a limit.
Okay.
So the rule, and this is a great time to introduce that, actually, I'll get to you, and if I forget, yell at me. Which is you can circle a number of ones so long as they are all logically adjacent, meaning no diagonals, no weird curvy angles. It basically has to be squares and rectangles. So using squares and rectangles, you can circle a number of ones equal to any value of 2 to the n. Meaning I can circle 0, right? Oh, sorry, not 0. That doesn't help. 1. 2 to the 0 is what I was trying to say. 2 to the 0 is 1. 2 to the 1 is 2. 4, don't write 6 because we all do this all the time. I don't know why. I make the mistake all the time that for some reason I write 2, 4, 6, 8. It's not. It's 2, 4, 8, 16, 32, 64, 128. If you lived through my generation, you had all the versions of Nintendos with those varying number of bits, so they're ingrained in your head. Anyways, so this is saying that as long as I have a square or a rectangle, I can circle that many of known ones. I am not allowed to circle 3 ones together. That is against the rules. Okay, your question.
Yeah, that's what I was gonna ask. If there's 3 zeros that are all adjacent, so I was like, well, what if you just circle that?
Not allowed. Because it's the same thing that I would need to add another of those extra terms, right? And there's not really a good way to do that on the K-map. And so we don't basically, there are other tools that simplify, but anyways, we're gonna stick here. Yeah.
So it's just like pairs of ones.
Yes. Sets of ones.
Is this what like the output where our output instead of a 0, 1 is an X? We can use that and circle ones with X's and just
Yes, we're
make
gonna
the
get
X a
there.
1?
Yes, we'll get there. You guys are so excited and gung ho. Let's get this done. I'm gonna pause all questions. I want to solve at least one of these. Okay, so now what it says is that these are all of my terms. There are 2 circles. I am going to end up with 2 terms. Okay, the terms are, we asked ourselves the question, in each of these circles, what doesn't change, right? What doesn't change? What's the same? So I go over and look and I say, well, in this row, A changes from here to there and B changes from here to there. So A and B both change. So the only thing that doesn't change is C. And then I say, or this guy, what doesn't change? Well, C changes, right? Because I'm going top to bottom, 0 to 1. C changes, that gets thrown away. I get an A and B, and then I go, look, what is A and B? A is a 0, not A, B. C or not A, B. Same thing.
So using this will directly help you simplify your truth table.
Yes, yes. This is a wonderful way to get a minimum sum of products representation of any truth table. It's nice. It is a minimum circuit. They are not unique, right? There are multiple possible ways to solve some K-maps. And that's the difference between an essential prime implicant and a regular prime implicant. Is a prime implicant is just saying there's 2 different ways to complete this K-map, okay? Yeah, so did you have a question? No, I thought I saw a hand go up over there. All right, this is all K-maps is. This is it. This is the greatest way to simplify logic. And then the great thing is now you see what the entire test question is, which is I would ask you the question, write a truth table for me to detect a prime number. Done. Now find a minimum expression for that truth table. Done. Now turn that into a minimum circuit. Done. Now turn that circuit into universal gates. Done. Oh. Done. Right?
Universal gates means NAND or more.
Correct. It is, right? We're engineers now. Now we can design any logic expression. I can give you a question. Design for me a circuit that is for your house. And in your living room, there are 3 light switches, and you want it to turn on anytime you toggle any one of those switches. Let's do it. Aha! Why did I erase my truth table? Two, 4, 6, 8. And in case you're wondering, no, I don't count rows every time for your benefit. I do it for mine because I'm really bad at that for some reason. A, B, C. L for light. Makes sense? Let's assume that the contractors you hired to put in your light switches were nice and they all started in the off position. They all start down. See, when you flip one up, you want it to go on, right? Okay, so 0, 0, 0, I want the light to be off, 0. Okay, now I go and say, well, if I flick a light on, I want it to turn on. And in fact, I flick any one of those. If I toggle, right, change from one position to the other, toggle, that's what toggle means. Any one of them, I want the light to turn on. 1, 1, and 1. That's that. I flipped any one of those, right? So this is just connecting this truth table to the physical story problem. Okay, and now any 2 of them, if I flick the other one on, it turns back off, right? Which is annoying. This is why we end up in these situations where the light switches are in stupid positions. Well, that's off, and that's off. And then we get a third one. That's the 1. So basically what we've done is we've ended up with an odd number detector. Right? That's all this really is. And then we draw the K map. I don't know if you guys notice how I draw these because it is actually really helpful, which is to just start dividing in halves, right? I always draw the middle one, then start splitting until they're there. I'm a terrible artist, if you can't tell, so I find little cheats like this. All right, people are writing, so I want to give everyone a chance so I don't lose them. I'm going to capitalize on the fact that I've already done a 3 variable input that I'm familiar with. So I'm going to write it in the same way, A, B, C, because now I know that my midterms fall as such. 0, 1, 2, 3, 4, 5, 6, 7. Right? I know where they are. I already did that. Those are my implicate numbers. So now all I have to do is start going down my row in numeric order according to the table. So it's 0, 1, 1, 0, 0, 1, 1, 0. Next half, 1, 0, 0, 1, 1, 0, 0, 1. Right? I had to flip the order of these 2 rows because it's binary. Always helpful to go in. It is not wrong to do it this format. I don't, because it requires more writing. That's literally the only reason I don't. These is my terribly drawn K-map. It's ready to go. Well, shoot. Nothing simplifies. This is the worst circuit. So I am allowed to circle 1. I go, I grab my pen, I circle each and every one because I need to complete coverage. Okay, coverage. That's the term. I have circled all of my ones. In order to get a minimum expression, if I ask for minimum expressions, that means you need to start by drawing the biggest circles you can and fill in the rest. Okay, That's pretty much, there's like a whole design rule list that the book has that you can go read, but it boils down to circle the biggest things you can find first and don't be afraid to try again. Okay, well, I called this L. Guess what? Nothing doesn't change, right? Because they're in this one spot, it doesn't move. So I end up with a sum of products expression with all of the variables in each of the terms. And then it's just a matter of going, well, it's not A, not B, not A, B, not C. That one is A, B, C, right? Because 1, 1, 1. And this one, A, not B, not C. I don't have to do any Boolean algebra because my K-map told me this is as simple as it goes. Okay. We okay if I erase this? Okay. I'm going to be smart this time, and I'm not going to erase everything. How about another familiar problem? Right? Senior officer, junior officer 1, junior officer 2. We want the missile to launch when the senior officer and either the junior officers have pushed their buttons. These two are the juniors. Are not helpful. So I know that only down here in this region, in this lower half where my senior is 1, can I possibly have a 1? And then I just look for where there are 2 1s. Now, senior officer walks in, he pushes the button. Junior officer walks in, pushes the button. Missile launches. The other junior officer pushes the button. Doesn't matter, right? No one cares. Missile's already launched. I don't care. I don't care what that spot is. X stands for don't care. Earlier, I called this A, this B, and that C, right? So I could use that same patterning to go and make sure that I don't do something really weird. But let's say I did. Let's say instead of putting C here, which was J1, let's say I put S here because I'm like the senior's all on his own, right? That makes sense. It makes sense to have the senior on his own line because he's the special one. Okay. And then I go, well, that makes this J1, J2, I guess, right? That's fine. And now I just have to say, well, 0, 0, 0, this is always the first square. It's never going to be anything different. The top left is always your first row. Okay, great. And now I just have to look at S is 0, J2 is 0, J1 is 1. Okay, so 0, J2, 0, 1. That's really annoying, isn't it? To go from here to there. So I'm going to change my mind and call this J2 and that one J1. I'm just going to flip them around because the one that I initially picked was bad, right? It's not that it's wrong, it's just that it was annoying to write. Okay, now I say S0, J2 is 0, and J1 is 0. So it's now 0, 0, 1. Ah, there we go. This is much better, right? Now they're adjacent in left to right fashion. Turns out I just go the other way, but I hate that. Now we look at the next one, 0, 1, 0, 0, 1, 0. It's still 0, right? Because I'm going to skip this one because we're gray coded. Next one is going to be that guy. He's still a 0. Next one is going to be 0, 0, 0. This is 1, 0, 0. 0. 1, 0, 1. 1, 0, 1. 1. 1, 1, 0. 1. Don't care. Now, remember how when you started simplifying this during the lab, that it helped to add an extra term, and it turned out that it was easier if we chose this one to be a 1 than if we didn't? This is why. This K-map visualizes why this was easier to choose 1. Because instead of having 2 circles that are on their own, meaning each implicant has 3 variables, with the don't care, I get to do this guy and that guy. Guess what? This is the same as just rewriting that term again. I'm just reusing him. It's fine. It's A or A is still A. That's all this circle does. That overlap, totally fine. I do not, if there was an X up here, I do not have to circle that. X's are not required to complete coverage. Only the ones. Okay.
But if that X on the bottom was a 1, you can't double up.
I can still double up with
Yeah.
ones.
Okay.
Yes. It's just that the don't cares are extra nice because if it's inconvenient, I can just pretend it's not there.
And if
So why don't you just have 1 circle for all of them?
Because 3 is not a 2 to the n option. Yep. You got a question?
if it was a 1, you'd have to circle.
You would
it.
have to circle it. But it turns out if that was a 1, then this is still the minimum expression because I wouldn't want to do that.
Right.
Because I can, if I can circle a bigger implicant, I must circle the bigger implicant in order to achieve a minimum circuit.
I mean, when the 1 was up there.
Oh, this?
Yeah.
Yeah, if this was a 1, then I would have to circle it on its own. Yeah. Creating its own implicant. Great. I have 2 different circles. That means I have 2 implicants. I have completed coverage. Now I can go write that. I guess L is still fine for launch or something. L for launch is equal to things that don't change. In case of the green circle, it is J2 changes, right? So J2 goes away. So when J2 drops, I have S, J1, S is 1, J1 is 1, no bars, or S, because we're on the horizontal axis, doesn't change. J1 changes, that means J2. J2 is 1s. Familiar circuit. You can then draw that, convert it to NAND gates, go throw it on a breadboard. This is why I flipped the order of lecture and lab this week. It's because it's kind of cool to see something that you've done in an easier way. Okay, now I've done story problems. I like story problems, right? It ties it to the real world of digital logic and thinking that way. Let's just start some arbitrary ones so I can start solving weird things. Don't forget this. I'm going to repeat it. Don't forget to gray code it because you'll get it wrong. Okay. Oftentimes, especially on exams and sometimes on homeworks, if I'm really good, I will provide you with the K-map because I want you to have specific ordered variables so that everybody answers end up the same, because K-maps are really hard to grade. That's all. Let's say we have this situation. This is a circuit. This is fine. I don't know what it does. We can find out though, right? We could turn this into a truth table. We can go the other way. Right? I would literally just go the truth table in order from top to bottom. If I order it as ABC, is 1 0 0 0 1 1 1 1. That's the order of the truth table. Okay. I grab my implicant. Remember how I said rectangles or squares? Because squares are rectangles anyway, so I could just say if it's a rectangle, you're fine. There. I have one more one. I could circle it on its own, but I'd be wrong because it is logically adjacent. Remember that wraparound question? That was a good question. There we go. I've completed coverage. Take a moment. Write me the minimized equation. If you have any of the implicants, you write the equation. Okay. Doing okay? Still working? Still working. All right. It looks like most of you are done. So here's our square. We asked the question, what doesn't change? I called that, I don't know, let's call it F. I made this one up, right? So F is the function. What is my first term? Anyone? Not B,
Not C.
not B, not C. So that would be this one. The C doesn't change as it wraps around. So it's a 0. So that's the not C. The B is here, 0 and 0. So it doesn't change. That's the not B. Perfect. What's my big square? A. So there's a pattern now, right? The bigger my circle is, the fewer terms the fewer variables I will have in each of my terms. I've been trying, I used to be really bad at this using the right vocabulary. If I have A and B and C, I have two terms with three variables each. Right, that's the vocabulary I try and stick to. That's the answer. Good job. Let's complicate it. We already know what the top does, 0, 0, 0, 1, 1, 1, 1, 0. Guess what? Same thing going down. Again, remembering that's 1, 1. If you want to start, I have some students that do this and go right for the 1, 1, the very first thing, so you don't mess it up. And now, your truth table would look like this, where there are now 16 rows, right? Because there's 4 variables. It's 2 to the 4, 2 to the 4 is 16. And now I'm just going to make something up. This is a trick question, but go ahead and take just a moment to just draw your implicants. Just draw your implicants. Don't solve it yet. Just go ahead and get the implicants circled. Yeah,
Circle zeros instead of ones.
we'll get there.
You can't wrap from the bottom to the top, can you?
All right. Most of you are looking up. Give me another couple of seconds. All right, if I can ask you all to be brave, would you all go ahead and just hold up a number high, hold it high, the number of, with a number of fingers equal to the number of implicants that this requires. Good, some of you got it. 2. So, this is the trick. See this? Those 4, 1 are adjacent, but this is a rectangle. I told you, it's a trick question. Don't feel bad, right? I haven't shown you something that complicated. It's just fun. That is an 8 min term implicant. That was a lot of simplification that you would have to write and go through with Boolean algebra. I think the rest of you probably got this one. All right, the vertical column. Yeah.
I'm just wondering, would you want to circle all 4 of them instead of just the 2 center?
Yes.
What does it change?
The number of variables that don't change, right? Because if I circle the inner 2, then D doesn't change, and A and B don't change, so there are 3. Whereas if I circle this whole thing, then that D does change from here to here, so it's just A and B. So it's actually removing one of the variables, which is why I say just circle the biggest things we can find and then move on from there. We now go ahead and just say, what is F? Well, I already said this one, right? That's just AB. Take a moment to write what you think the big chunky 8 one is. Well, going across, if I go all the way across, that eliminates both A and B. Now, top to bottom is just a question, well, C does change, D doesn't. So we know the thing that changes goes away. D, then we just ask the question, is D a 0 or a 1? D was a 0. It didn't change, not D. Turns out that C doesn't matter to this. C is a useless input. Let's do another, I think one more of this just for practice. It's like, I want to write that one. And again, if you're a bad drawer as I am, I just start dividing it in half. I get 16. Right, and I'll just point it out again, right? Like this row is equal to C and not D, right? It's the same thing. I just use 0 and 1s to be faster so that as I draw a million K maps this semester, I don't have to write as much. Okay, go ahead, take a moment, circle your implicants. All right, let's be brave. Everybody hold up a number of fingers equal to how many implicants I need. 2. Yep. Yeah, you pulled the 2 to the 6 or 2 to the something is 6. Yeah, I do it all the time. Don't feel bad. It is 2. Right. the easier of the two being this one. And then the hardest one to see, of course, being the weird four corners.
You have to do the top ones. Okay, just do the bottom two.
You do all four corners of the figure, so you'll eliminate them.
Yes. So if I do just that one and that one, I get a expression for this, but I do not get the minimum expression for this circuit. So did anyone get the four corners? A couple of you, good job. Yeah, and then take a moment, write out what you think the f is the function. Did I do that right? I'll make you guys start checking my work now. You see now why I'm trying to like make a bigger deal about an alphabetical ordering of your variables, is because otherwise each one of you is going to get a different permutation of this, and grading it gets become a nightmare. That's why I don't really care if they stand the order of the terms, but the variables within each of the terms should be alphabetized. Now it turns out, right, this one we could change the circuit. What's nice, the sum of products will always result in, sorry, circling the ones will always result in a sum of products, which is AND gate feeding into an OR gate, right? It will always get that form. In this case, I could factor out the not B, but then I get a product of sums expression, right, where the output again is AND. What if I want a product of sums and I can't guarantee it using like a simple modification? What do you think I do? I circle the zeros. So let's circle the zeros. Oh, does anybody need me to walk through that expression? That makes sense to everyone? Okay, all right. The zeros, realistically, right, given a circuit, if you don't care if it's a NAND or NOR, right? Because this is actually what it's really doing for you, is if I am circling the ones, I'm making it very easy to design a NAND-based circuit. If I am circling the zeros, I'm making it very easy to make a NOR-based circuit. This is how the K-map ties in very tightly to your circuit design. So these two zeros stand on their own, but I'm going to go for this. I'm going to illustrate something after I circle. So I get 4 there, nice and easy. I get 4 here, nice and easy. Now, the catch is I'm done there, right? I've circled all the zeros. I have completed coverage. Don't, for now, circle that dashed, right? That would be an extra implicant. I don't need it to complete coverage. It's not necessary. But later, next time, we're going to come back around to this and we will add that, because sometimes the minimum circuit causes problems, it turns out. But we have to introduce like a more methodical way to start talking about gate delays, because it turns out that's what this problem occurs, is when gates have delays, this is an issue. But we'll come back to that. For now, we'll circle the zeros, not worry about that extra little guy. And now have to write the expression for this circuit. I've circled it, I got coverage. But the next step is different than the sum of products because I'm generating a product of sum circuit, right? I've already alluded to that. And so it's going to be written as a product of sums. However, we're still going to start with what doesn't change. And I'm going to say, let's start with this one. He's actually a little easier to see because he's self-contained. And we say that A doesn't change, C doesn't change, D doesn't change. So I have not A, not C, not D. However, remember De Morgan's, how I flipped the gate and the variables? I have to do the same. So now this guy doesn't like ones. Let's say that he doesn't like ones. That means this first term that would normally be, what did I say? A or C or D. No bars, right? Because they are all 0. That's where most of the confusion comes in, right? Most of you will get the form right, because remember this is product of sums, but you'll forget to flip the variables as well as the gates. Or it looks like I'm gonna have to do a new row. This guy, well, this is gonna be easier. It's just gonna have 2 variables in it, right? In fact, because of that, it turns out I'm gonna be able to fix this. So I really mean and, right? Because last time it was or, now it's and. I need A or C or D, and let's check out this guy. C changes, D doesn't. A changes, B doesn't. So that means I've got B or D. Yeah, I'm just starting. I just start with what the variables are, and then I go and check whether they have bars or not. And so that's ones, those are ones, they both get a bar. Okay, last one. Well, we've still got D, right? We're on the same 2 rows, so D is going to be the same. And it's still going to be that not D. And then we come over here and say it is A. That doesn't change. And it is also a 1, not A. Yeah.
Wondering, is there sometimes when it's better to use more gates than NAND gates? Like in this case, would it be better to use?
Yes, and sometimes it's going to be informed by what circuit technology are you trying to build this in, and sometimes it's going to be informed by, well, I have both of them, what one's easier? Because like this one would be, that's 3 and terms, this would be a implicant there, 2 here, and 4 there. It's actually very close to the same. I think it maybe is mid simpler. I think 1 variable simpler. Because in the with the ones they are, nope, never mind, that's just 2. So no, it's identical. Because I get a 4 there, a 4 there, and 2 here, so the complexity is the same. Some of the textbooks make a big deal out of that, like design a minimum complexity circuit given this truth table, and then you have to make the decision. But I don't really focus on that because most of the time it's technology driven. And ultimately, it turns out you guys aren't going to be doing K-maps as like a career. The reason we talk about them is it turns out it's a really good tool to visualize what we call hazards, which is we'll talk about next time. And it also helps you understand what the computer does when it simplifies circuits for you and why that can cause problems, which is what we'll talk about later. Because it's useful to think about what the computer is thinking that you're thinking, right? Because there's often that disconnect between I thought I told the computer to do one thing, it's being really weird, and it turns out you just told it wrong. Well, you have to think about how computers think, and they do things like use algorithms like this. Computers use different algorithms generally, but they can do K-maps. Yeah. Anyways. I guess I should do one more with the don't care. That's a good one. Yeah, that's a good one. Take a moment to start circling implicants as well. I think you guys can handle that. Let's do ones. Let's just go back to ones for this big don't care. In fact, maybe we'll repeat for the zeros. We're running out of time. You guys asked a lot of questions each of time, but I love it. Don't think I hate your questions. It's actually really engaging. It just means my timing is a little off because normally you guys are really quiet, actually. I think it takes 3 implicants if that helps. Looking like that, it's hard to do in my head.
Wait, I thought we can't do 3 implicants.
An implicant is a circle. I can't circle 3 min-terms,
Oh, right,
but I can have 3 implicants. Yeah, yeah. Notice how some of this class is just like a vocabulary quiz, but hidden beneath it. Turns out all those annoying vocabulary quizzes in elementary school are helpful.
I think if you got midterm on your elementary vocab quiz, you got other issues.
All right. So again, I'm just going to look for big ones to circle, and sometimes you'll later find out that you didn't need all of the big circles that you made, and that's fine. I don't think that's going to happen here. There's a big obvious one in the middle, right? I like that min-term, or sorry, that implicant. And then this also covers a lot. Oop, I guess I need 4 implicants, don't I?
Yes.
Okay, that's okay. I'm not good at visualizing things. I'm not an artist. Whatever, I'm going to reuse some colors. So this one, that one, I don't see any way to get more than 2 for this guy, but this one I can do. And then this one, I'm unfortunately just stuck with those 2. I don't have to worry about this X or that X. It's not doing anything useful for me. They're just hanging out. With the function, I like the long rows. They're easy for me to do, right? Because it's just C and D, and it's not C, so not CD. Next, the red circle is going to be D. So B and D, because B doesn't change. The green square is also going to have a D term in it, but this time it's going to be A. And then my last one, right, he's going to have 3 variables because I only circled 2. And so over here it's the C that doesn't change, and neither A or B. So A and B. I said C, sorry, right? C. And it's 1. So there we go. It looks like I'm writing for a horror movie. Okay, it would be good practice to keep this in mind, go home and do the zeros, talk to each other, see if you get it right. Right, you can converse with each other and find out if that's the minimum expression. That's don't cares, that's zeros, right? Don't cares occur anytime something can't happen, shouldn't happen, or doesn't make any sense. Like, why is that a thing, right? So those are don't cares. The shouldn't happen is a little bit iffy, right? Because what I mean is shouldn't, like you have a scenario like if it's going to happen, but if it does, I don't really care what happens, right? That's what don't care says. I don't really care what my output does in this scenario. It's just, there's a possibility, a reasonably strong possibility that I'll ask you a story problem in the exam that is scheduled for February 15th, like 16th, I think, for you guys. February 16th, I think, is your exam. It's on the calendar, should be on the website. It's going to basically be through this lecture and next time. That'll be all the material. We'll have at least half the class worth of review before the, what is today? Is today Wednesday?
Yeah.
Yes.
Okay, kind of weird. So we'll do the review the second half of class on Wednesday, and the exam will be the first half of class on Monday. So you'll have the review and then the weekend to study, and then the exam will be Monday. Make sense?
And
Okay.
Remind us, are you gonna have the exams here? Or we do testing centers or anything?
We'll do them here. If you end up sick or unwell, you can actually go take it from home. Don't bank on taking it from home. Try and be here because statistically people do worse at home. I'm gonna have to really think about this situation. The reason I don't want to do the testing center because a lot of crazy backlog and it's just a nightmare for everyone involved, to be honest. Normally what I do is it's open notes, open book, open whatever, I don't really care. This is a bit of a weird situation because not everyone has the book. And that makes it hard for making it balance between those in person and those remote. So what I think I'm gonna do is that those in person, I'm just gonna say open notes. So take whatever notes you want out of the book, bring them in, get them organized. It's good study anyways. When people take a remote, I can't monitor them well enough. So I'll curve separately. There's enough students because I'll just pile you guys and the other class. I have over 50 students combined. That's enough that I assume there will be enough of you with COVID by that point that, that I think I'll be able to generate a decent curve between the two. I'm not sure yet. This isn't gospel yet. I'm just kind of thinking out loud because sometimes when I say something out loud to people, I realize how stupid it sounds, but I think it might have to be what I do. I talk to think. I'm sorry if it annoys you that I do that, but it's who I am. Yeah, we can go ahead and wrap up here. We'll brush up on some K-maps. We'll do some review next time. I'll post the homework as soon as I can. I recommend diving into that as soon as you can, right, to get your hands on some K-maps before you have time to forget how they're done. It's okay to use K-maps to check your answers in the Boolean algebra. You will be asked Boolean algebra questions and you'll have to show your work. If you're thinking you're going to take it from home and go use an online automatic K-map solver, because those exist, get that out of your head because I'm going to design them as a trap because it turns out the computers are really easy to trick and you'll get a result that only a computer would generate because you'd have to be a madman. So I'm going to trick the computers into revealing that you're using generators. And yeah.
In one class, invited terminology about us. What are the gray coded?
Gray code.
No idea. I just thought like K-maps had a stupid order on them because he told us the order